Hey everyone, let's continue on with our look at isotopes and start thinking about average atomic mass. So it's really rare that we would have a situation where we dig an element out of the earth and all of the different atoms of that element would have the exact same mass. And why is that? Because different isotopes of different atoms have different numbers of neutrons. And if you have different numbers of neutrons, that's going to change your mass. So let's figure out how we can figure out the average mass of a given set of isotopes for a given element. And in particular, I want to revisit what we talked about in terms of AMUs, or atomic mass units, and how that was derived based off the carbon-12 atom. So here's what we know about the carbon-12 atom. Carbon-12 has a grand total of 12 protons and neutrons put together. It has 6 protons, 6 neutrons, add those up, grand total of 12. We also know from the periodic table it has a mass of 12.01 grams per mole. We also know that a mole has 6.02 times 10 to the 23rd things in it. So we can do some math with that, and we can figure out that the mass of a proton is 1.673 times 10 to the negative 24th. Neutron is similar, and electron is much different, right? We said this is about 10,000 times later. So this is all based off of the carbon-12 atom, but those are some nasty numbers, right? So there's got to be a nicer way to do that, and that's why we have these things called AMUs, or atomic mass unit. And so we say that a proton has 1 atomic mass unit, a neutron has 1 atomic mass unit, and because electrons are so inconsequential compared to the other two, we give them 0 atomic mass units. So how can we utilize that in order to figure out what the average atomic mass of different isotopes is? Well, first off, remember that carbon-12 has 12 things in its nucleus, protons plus neutrons, so we're going to give it a mass of 12 AMU. Carbon-13 has 13 things, we're going to give 13 AMU, etc. But we might get more specific. So sometimes you'll see atomic masses that look like this, that have a little bit more in the way of significant figures, right? So they're a little bit higher level of precision in terms of the decimal points, but you'll notice they're really darn close. So 34.696, that rounds to 35, 36.966, that rounds to 37. So they're very close to the isotopes that they represent. The other thing we should be aware of is the abundance of different elements in the earth. So if you take one of these giant shovels that you see on the bottom and you dig out some elements, you're going to see different elements, of course, but for a given element, let's say carbon, for instance, carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. And it's not that they all exist equally 33.33% of the time. Some occur more likely than others. So let's say that you have a given isotope and it has a percent abundance, that's how often it occurs, of 56.20% in nature. Just be mindful that when we use this in math, we're going to turn it into a decimal point. So 56.20%, percent equals per 100 or over 100. That becomes 0.5620. So let's utilize that to our advantage. I'm going to join you on your note guide. We are going to do some practice problems. Let's start off with copper. Copper, we're told, has 2 naturally occurring isotopes. It tells us both their relative abundance, right? So it says copper-63 happens 69% of the time. Copper-65 happens 30.85% of the time. And we want to figure out what the average is. You'll also notice they give us very specific masses. So let's deal with that copper-63 first. Copper-63, we're told, actually has a mass of 62.929601. Someone got pretty excited with sig figs. And we were told that it occurs 69.15% of the time. So we're going to take that and turn it into a decimal. 69% becomes 0.6915. We'll solve here in a second. Let's also worry about that copper-65. So copper-65 also has a mass. It's written right there above. You can see it, 64.927794. We're told that it occurs 30.85% of the time, 0.3085. You don't need to do this in your calculation, but you can notice that if you add these two together, 6.6915 plus that, it equals 1. right? And that makes sense because you want to be making sure that you incorporate all of your isotopes, so this should really equal 100% or 1.0 as a decimal. We again can solve, so let's solve both of these. The purple one, when you do the math, is going to equal 43.52. The blue one, when you do the math, is going to equal 20.03. Let's add those together, and you will get 63.55. And this has units of AMU, which is atomic mass units, or grams per mole. And if you look at your periodic table and you look at copper, 63.55 should look pretty darn familiar, right? So that is that average atomic mass that's written underneath copper. And this explains why it's a decimal, right? The reason that this is a decimal and not a whole number is because it's an average of different isotopes. And more than an average, it's a weighted average based on how often they occur or their relative abundance. So we can do straightforward problems like that where we are given masses, we are given relative abundances, we multiply, we add together, but we can also make this a bit more complicated. So check out number 2. If you want to pause and read, feel free, and then you can rejoin us. If you've rejoined, you'll notice that we are told that carbon has 2 common isotopes, carbon-12 and carbon-13. It turns out that carbon actually has a third isotope, carbon-14, but for the sake of this problem, we're just going to ignore that one because it's so small in percentages. We are told some information here, right? We are told carbon-13's specific mass, 13.003355. That is right here. That's carbon-13. We're also told that there's carbon-12, and we're told that it has a percent abundance of 1.07%. And now we have to figure out the actual mass of carbon-12 in AMU. So we're basically looking for what that mass is specifically, kind of like this number, this 13.003355. There's a piece of information that's not given in this problem, right? And the piece of information is that carbon has a molar mass, right? And you can look on the periodic table and you can find it. And once you do that, you will notice that carbon's molar mass is 12.01. So we're going to get tricky with our math here, but I think you can follow along. So carbon has a molar mass of 12.01. In problem number 1, we were solving for that answer, right? We were solving for that number that shows up on the periodic table. So how did we get there? Well, we took the mass times the relative abundance of the first isotope. So let's pretend we're dealing with carbon-13. The mass of carbon-13 was given in the problem. It's 13.003355. And we were also told that that isotope occurs about 1% of the time. So in decimal form, 0.0107. That's how often carbon-13 occurs. Now, we're not told how often carbon-12 occurs, but because we made a choice here to ignore carbon-14, that means that the grand total of carbon-13's relative abundance, which is 1.07%, and carbon-12's relative abundance must equal 100%, or in decimal form, it must equal 1. So if I take 100 minus this 1.07%, that means that the remaining 98.93% must be carbon-12. Again, we're ignoring carbon-14. So we can use that in our calculation, right? The total mass on the periodic table is equal to the mass times the relative abundance of carbon-13 plus the mass, which we don't know yet, right? So that's our x, times the relative abundance of carbon-12, which we just said is 0.9893. Again, if you're wondering where we got that, that comes because these two numbers, let me just show you really quick, this number and this number must equal 1, right? The relative abundance must add up to 1 if we're accounting for all of the different isotopes. Now it becomes as simple as solving for x. So there's a little bit of work we should do. Let's combine these terms. So we'll have 12.01. When you do this multiplication, you get 0.1392, and that is still added to our 0.9893x. We can then subtract across the 0.1392, right? So when we do that, we will get 11.87, and that is equal to our 0.9893x. And when you solve this for x, you will get an answer of 12.00 grams per mole, or AMU, which makes sense, right? It makes sense that the mass of carbon-12 is very darn close to 12.00 AMU. All right, so we've taken things up a notch in number 2. Let's try number 3. If you'd like to try number 3 on your own and then rejoin, feel free. There are going to be some extra wrinkles here, but you'll notice we can get through it. We can make this happen with our problem-solving skills. So let's talk about gallium. Gallium is also on the periodic table, and there's something you should look up on the periodic table before we even begin. So gallium has a molar mass, and I'm just going to write it over here. Gallium has a molar mass from the periodic table. If you go and you find Ga, gallium has a molar mass of 69.72 grams per mole. And we know some things, right? We know that that is going to be equal to the mass times the relative abundance of the first isotope plus the mass, let me put this in a different color, the mass times the relative abundance of the second isotope. And better yet, they tell us what isotopes we're dealing with, right? So this blue one, this first isotope, let's make this one Gallium-69. So they say that's Ga-69. And let's make this pink one Ga-71. And then they give us some information about both of those. So let's see if we can fill in what we know. We know, again, the molar mass from the periodic table is 69.72. That's the total for gallium. We have been given in the problem the mass of gallium-69. We're told it's 68.9257. Where relative abundance is what we're looking for. The main goal of the problem is to figure out what's the percentage of each of these isotopes. So let's call that x. Plus, we know the mass of gallium-71. It's 70.9249. We're also looking for its relative abundance, but chances are it's not the same as the blue relative abundance, so let's give that y, right? And so now you say, well, we got a problem here. We have an equation, but it has two unknowns. We have one equation, two unknowns. That doesn't work, but we know something, right? Because we are in decimal form, we know that the relative abundances of gallium-69 and gallium-71, they must add up to 100%, or in decimal form, 1.00. So that means that my relative abundances that I wrote down over here and over here must equal 1 when they're added together. And you'll notice we made the blue one x, we made the pink one y. So another thing that we can do here is to say that x plus y must equal 1. We know that, right? We have to account for all of the isotopes. So that means if I solve this for one of those variables, let's just solve for y. Y is equal to 1 minus x. So let's plug that in and see where we go, right? If I plug that in for y, let's just rewrite everything. So we have 69.72 is equal to 68.9257 times x plus 70.9249 times what we just solved for as y, which is 1 minus x. Now we have one equation, and now we have one variable. It's x. So we have to get a little creative here with math, right? We have to expand. Let's go ahead and rewrite everything out. We now have 69.72 equal to 68.9257x. Nothing has changed there. Let's distribute this one out. Plus 70.9249 times 1 is just 70.9249 minus 70.9249 times x. So now in one step, you can do this on your calculator, I am going to combine the 69.72 and this 70 by subtracting them, right? So I'll do that in purple. And then in another color, let's do orange, I will combine 68.9257x and 70.9249x, again by subtracting. So when we do all of that, and hopefully you can check this on your calculator, you get 1.2049. 1.2049 is equal to 1.9992x. So then finally, if we solve this thing for x, we will realize that x is equal to 0.6027. So what does that mean? Well, x, you'll remember we gave up here originally to gallium-69. So what we're saying is that gallium-69, this is Ga69, occurs, we don't want this in decimal form anymore, we want percentage, so it occurs 60.27% of the time. And then we can simply figure out the other one, gallium-71, by some subtraction, right? So over here we said that y is equal to 1 minus x. So let's just do our math again over here. Y is equal to 1 minus what we just solved for as x is 0.6027. That means y is equal to 0.3973. That one was gallium-71. So this is gallium-71. We want it in percentages, so this should be 39.73%. So our final answer is that gallium-71 occurs 39.73% of the time. Oops. And gallium-69 occurs 60.27% of the time. So obviously quite a bit of math there, but doable, right? So you can keep your wits about you. The keys that we had to get that weren't already given in the problem were the fact that we have 69.27 as the molar mass of gallium, and we can figure out that the two relative abundances added together have